Hi guys, welcome back from break, and we want to start Unit 3, which looks at intermolecular forces and properties. And so today we want to talk about intermolecular forces. Now, the thing to remember, there's intramolecular forces versus inter. So inter, remember, interstate is between state. So intramolecular forces are bonds. Those are ionic bonds or covalent bonds or metallic, like we talked about in the last unit. These are going to be much stronger than the intermolecular forces that we'll talk about today. However, intermolecular forces are probably mostly responsible for most of the physical characteristics of a substance, like its melting or its boiling point. So what we're going to do when we talk about the intermolecular forces is we'll start with the strongest and then kind of go to the weakest, or the one that everybody has. So an ion dipole, this is going to be the strongest type of intermolecular force. This is going to happen when an ionic compound dissolves in water, basically. And so if you read a prompt and it says salt is dissolved in water or some ionic compound is dissolved in water, you're going to have an ion dipole force. And so what will happen is that your ionic compound will ionize, break up into its positive and negative ions, and then your polar molecule, the more slightly positive part of a water molecule, will surround the negative ion. The more negative part, or the oxygen end of a water molecule, are going to surround the positive ion. So an ion dipole force. Here you see sodium and chlorine. Sometimes you're going to be asked to draw this. And so please pay attention. Your chloride ion is your negative ion. So please make sure when you orient your water molecule, you put the more positive hydrogen ends of the water molecule around the negative ion. And then make sure with your sodium positive ion, you put the bigger oxygen end surrounding the positive ion. Looking at ion dipole and Coulomb's law, basically the force is going to increase as the radius of the ion decreases, because the denominator will get smaller, the force will get bigger. If the charge of the ion increases, the force of attraction will also increase, and the magnitude of the dipole on the polar molecule increases. So if something is more polar than something else, then that force of attraction will be greater. A dipole is the third strongest type of intermolecular force. And this is what happens between polar molecules, water molecules next to other water molecules. Molecules with dipole moments basically experience Coulombic interactions when they're close to each other, right? If it's polar, there's a negative end and a positive end. It's going to be attracted to, the negative end is going to be attracted to the positive end of like another polar molecule. The positive end is going to be attracted to the negative end of another polar molecule. Looking at orientation, when positive and negative dipoles line up, attractive forces are stronger and repulsive forces are weaker. So this statement is a good one to kind of remember about why one structure may be better than another. So you want a structure where the attractive forces are maximized and the repulsive forces are minimized. When the positive and the negative dipoles do not line up, the attractive forces are weaker, repulsive forces are stronger. We do not want this model. Hydrogen bonds are a type of dipole-dipole. So usually it's helpful if you have to identify the intermolecular forces in a FRQ prompt or something like that, and hydrogen bonds are present. I always encourage students to mention dipole-dipole and hydrogen bonds. And so the thing to remember about hydrogen bonds, it's going to occur between a hydrogen that is covalently bonded to fluorine, oxygen, or nitrogen. Only those three. And another fluorine, oxygen, or nitrogen with at least one lone pair. It is 5 to 10 times stronger than other dipole-dipole interactions. So it's kind of a big deal, okay? How come hydrogen bonds are so strong? Well, fluorine, oxygen, and nitrogen bonded with hydrogen, they are very polar. The electronegativity difference is very high. These atoms are small, so the partial negative and the partial positive charge caused by the differences, they're very highly concentrated. And then the lone pairs on fluorine has 3 lone pairs, oxygen has 2 lone pair, and nitrogen generally has 1 lone pair. It increases the already partially negative charge on the atoms. So anything with hydrogen bonds is going to have a higher boiling point or a higher melting point, even than something with dipole-dipole intermolecular forces. A lot of times you'll be asked to show the interaction or draw the line that's going to show bonding between water molecules. So remember, our oxygen end is our partially negative end, our hydrogen end is our partially positive, and so it will be a bond between hydrogen and oxygen with the negative end and the positive end properly oriented. So make sure you understand the orientation of the molecules in a hydrogen bond between water molecules. Basically, hydrogen bonding is the reason that water has a relatively high boiling point. This shows you hydrogen bonds between water and methanol. So notice we have a hydrogen bond here between oxygen and hydrogen. Again, oxygen and hydrogen again, oxygen and hydrogen. This area over here is available to continue hydrogen bonding with more methanol. When you basically add alcohol will dissolve in water. So when you add alcohol to water, the hydrogen bond changes. So substances that have like intermolecular forces are soluble in one another. 2 different molecules that form hydrogen bonds will dissolve in each other. Looking at actinide, it actually forms 2 hydrogen bonds with itself. Because this structure can form 2 hydrogen bonds, it's going to have a higher boiling point than water. So notice the boiling point's 221. And so if you're ever asked about why, the reason something is going to have a higher boiling point than something else is because A, it might be bigger, but look for hydrogen bonding first as a reason why a boiling point is significantly higher. This actinide, not only can it form 2 hydrogen bonds with itself, it's also bigger. So it's going to take more energy to make it go into the gas phase. This ethanol does not form any hydrogen bonds. So notice the structure of this. The hydrogen is bonded to a carbon. Hydrogen needs to bond with fluorine, oxygen, or nitrogen in order to form a hydrogen bond. Looking at boiling point trends for different molecules that form a covalent bond with hydrogen, when you move down a group, basically you'll see that the molar mass of the overall molecule increases. And the molar mass is going to increase because the central atom, the mass of the central atom increases. So you should see the trend that the boiling point increases slightly as the mass increases, because it takes more energy to push it into the gas phase. The molecules are larger and they're more polarizable. So we're going to look at that term a little bit. But there's going to be some exceptions. So you may be shown a graph like this and it's like, hey, What's the overall trend? The overall trend is that boiling point increases as mass increases, but there's three big exceptions to this. Well, that's not an exception because we have a big increase here. So the two exceptions are going to be group 5 and group 6. And water and ammonia have a much higher boiling point because they are the only molecules in this graph that can form hydrogen bonds. And it takes a lot of energy to break the hydrogen bonds. So be on the lookout for hydrogen bonds as a reason why a trend is busted, kind of. Basically, when we looked at chemical bonding, looking at potential energy, this is the same concept. Potential energy is going to decrease as the molecules are pulled closer together by their intermolecular attractions, and the same amount of energy must be added to pull them apart. So the more polar the molecule, the stronger the intermolecular force and the lower the potential energy. Okay? So the more polar, I'll say that again so you can kind of take a note on that. The more polar the molecule, the stronger the intermolecular force of attraction and the lower the potential energy. Molecules with stronger dipoles have stronger attractions to each other, and the potential energy is going to decrease as the molecules move closer together. Energy has to be added in order to weaken or break the bonds, so potential energy will increase as the molecules move away from each other. A dipole-induced dipole, basically a polar molecule will induce a dipole on a nonpolar molecule. The electrons in the nonpolar molecule are going to be attracted to the positive end of the polar molecule. This will cause a temporary increase in the electron density in the nonpolar molecule. It does not stay. The electron density, the extra electron density, will only remain on the side of the molecule that points toward the positive end of the polar molecule for a brief moment of time, because those electrons continue to move. So basically a moment later, they're going to realign. This increase in electron density is only temporary, but it's constantly recurring. So this type of attractive force produces a small series of tugs. So the small tugs basically sum up to an overall net force of attraction. But the attraction's small, it's constantly kind of being turned on and off. So this is the type of force that happens when oxygen gas or nitrogen gas, definitely nonpolar, when they are dissolved in water. So basically, we will talk about larger, more polarizable molecules later. So we're going to talk about London dispersion forces. So this is just kind of an information type of thing. Induced dipole, we don't even really use this term. We use the term London dispersion forces, or you may see it as LDF, London dispersion forces. Everybody has London dispersion forces. So these forces exist between all species. So if something has hydrogen bonds, you can say, oh my gosh, this boiling point is so high because hydrogen bonds are present. So when you mention hydrogen bonds, also mention dipole. And then everybody has London dispersion forces. So you can say if there's hydrogen bonding, you can say forces present include London dispersion forces, because everybody has those, dipole, and the special case of dipole with hydrogen bonding. And basically, if you have two nonpolar species, if you take a nonpolar solid and you dissolve it in a nonpolar solvent, you're only going to have London dispersion forces. And it's because of those temporary induced dipoles from neighboring species, basically. So London dispersion forces, we're going to call them. And this kind of shows you sort of what it looks like. So if you were to take an overall average of the electron density of a nonpolar species over time, you would see that that the electron density is evenly distributed. But at any one moment, look, time, 0.1 second, at any one moment, the electron density can be concentrated on one side or another. So it's like momentarily positive. So basically, look, right now, this at any instantaneous time, right, it's polar, but then it's not. Okay, averaged over time, the atom is nonpolar. So but instantaneously, it is polar. So London dispersion forces. Atoms, molecules, or ions that are close together will have London dispersion forces. So everybody, remember, everybody has London dispersion forces. Species that have more electrons and larger electron count, we're going to use a new term. We're going to say they're more polarizable, okay? More polarizable means it's going to take some more energy to move them into a gas phase. They'll have a higher boiling point because they are more polarizable. So species with more electrons, larger electron clouds are more polarizable. Again, remember, more polarizable. They have a weaker hold on their electrons. Remember, when we move down a group, those electrons are farther and farther away from the nucleus. So the more electrons a species has, the more polarizable it is. This is as we go down a group. This is not always true when you go from left to right, because you remember the atomic radius decreases, and so the electron cloud is actually smaller. But molecules are definitely more polarizable as you move down the periodic table. Looking at molecular shape, so basically molecular shape is going to play a role in the strength of the London dispersion forces. This is an example of an unsaturated fat, okay? Saturated fat is straight and solid at room temperature. So when I was in organic chemistry, I always remembered saturated, straight, and solid. So saturated fats are solid. Unsaturated fats have a double bond between at least two carbons in the chain. So basically, this is going to produce, it's now 3 charge clouds, so you're going to get a trigonal planar geometry around each of those carbons where the double bond is, and that will bend the molecule. So unsaturated fats are bent, and they stack up. It's like putting a bunch of coat hangers together. And so saturated fats stack up in things like your arteries, and they're super bad for you. So that is kind of the deal with unsaturated fats. The food industry likes saturated fats, or actually these guys, your saturated fats are going to stack up because they're straight, right? The food industry likes saturated fats because they're not easily oxidized. So, looking at dispersion forces are going to increase as the contact area between the molecules increases. So stronger dispersion forces in your saturated fat, right? Because they're flat. There's lots of areas where you can do some, there are points of contact. Looking at pi bonds, that would be our double. Remember, we have pi bonds. We have sigma single, so pi bonds are in double and triple bonds. So the presence of pi bonds is going to increase polarizability. So the electrons in those pi bonds are more delocalized, so they can move and assist with polarization of the species. So if we kind of look at the general trend about the relative strength of intermolecular forces, you'll notice our stronger ion-ion, ion dipole when we dissolve an ionic compound in a polar usually water, okay? Hydrogen bonds, notice, hydrogen bonds are our strongest dipole-dipole. And then generally we don't look too much at these. We kind of lump all of these into a London dispersion forces. So usually we'll say that we have ion-ion, ion-dipole, hydrogen bonding, dipole-dipole, or London dispersion forces. But this is going to help you decide if you have to choose between two species, which one's going to have a higher or a lower boiling point. So, for example, which species has a higher boiling point, C2H6 or C3H6? So when in doubt, just draw the Lewis structure. So we don't have any hydrogen bonds in place. So this guy's bigger. It's bigger, it has more mass. So the larger molecule, both of them are non-polar. The larger molecule has the higher boiling point. Larger molecules are more polarizable because they have more electrons. And we only have London dispersion forces because these are non-polar. So you'll have one of two situations. You'll either be asked to predict which one will have a higher boiling point and justify your response, or you will be given the boiling points and asked why they are different. Now, be careful when you have negative numbers. Remember, this boiling point of negative 42 is actually higher than this boiling point of negative 89. You'll notice that the boiling points of both are not really very high because the molecules are non-polar and they only have London dispersion forces, especially when you compare it to something like water with a boiling point of 100 degrees Celsius. All right, here, which species has the higher boiling point? All right, C3H8 is non-polar. Is our molecule over here? Is it polar or is it non-polar? So I believe our molecule on the left should be polar. Our C3H8 is non-polar. So our polar molecule, what kind of intermolecular forces? We know our non-polar, you should be saying if it's non-polar, it only has London dispersion forces. So over here I see some lone pair. So what can this do? This can probably hydrogen bond, right? So I would say dipole-dipole, hydrogen bonding, and London dispersion forces. Whereas our non-polar molecule is only going to have London dispersion forces. And so who would have a higher boiling point? Well, this polar molecule, I would say, is going to have a higher boiling point because it's going to take more energy to disrupt these hydrogen bonds. So let's take a look. Our boiling point of CH3, CH2OH is 78 degrees Celsius, while our C3H8 is 42. All right, let's try again. Okay, this guy over here, this guy's polar. All right, how about over here? Is this polar or non-polar? Well, my central carbon is attached to different stuff. And there's some oxygen. So I'm going to say that this is polar. I'm going to say that they're both polar. All right? So if they're both polar, we can have, it looks like we can have some hydrogen bonding. We can, but there's two oxygens here. So we can actually have more hydrogen bonding on this molecule than we can on our guy over here. And so we'll have hydrogen bonds and London dispersion forces, but here we have twice as many opportunities for hydrogen bonding as well as London dispersion forces. So I would predict that this guy, who's bigger, A, who's polar, and has twice as many opportunities for hydrogen bond, will have the higher boiling point. And we notice that it does indeed have the higher boiling point. Okay, which has the higher melting point. Okay, same kind of principle. All right, my CH4, is it polar or nonpolar? I say nonpolar. My Cl4 is also nonpolar. So what are we going to look at if they're both nonpolar? We should, what forces are present? Nonpolar London dispersion forces for each. So now let's take a look at size. Which one's bigger? Well, iodine is bigger than hydrogen, and so CH4 is smaller, less polarizable. Ci4 is larger and more polarizable. And so Ci4 should have the higher melting point. And you'll notice that is indeed the case. All right, which one has the higher boiling point? Woohoo! Okay, I have an ionic compound, right? And a polar molecule, okay? Ionic and polar. So what forces? You have ionic bonds, and in water, you have hydrogen bonds and London dispersion forces. These are intramolecular forces. These are intermolecular forces. Because of that, our ionic bonds are going to be a lot stronger than our intermolecular forces. And you'll notice that the boiling point of sodium chloride is much higher than the one of water. And so it's important, if you're doing an FRQ, to mention that that would be because the intramolecular forces are stronger than the intermolecular forces. Something that's really cool is that this is how your proteins are actually constructed. And your proteins have a carboxyl end and an amino end. And so hydrogen bonds are going to form between the oxygens and the hydrogens within the same chain. And so this is going to set up your secondary structure of your proteins. And then tertiary structures are basically going to be caused by intermolecular interactions between R groups. If you denature a protein, you're going to break down its tertiary structure. You're going to break these London dispersion forces and even your hydrogen bonds. So if you have a really, really high fever, that provides enough energy to break down some of these intermolecular forces in your proteins. So that is it on intermolecular forces. Check out your homework assignment, and as always, let me know if you have any questions.